I guess I'll go ahead and get started here. First, my name is Sam Rash. I'll give you my 30-second background spiel. I've been working in distributed computing and bash systems for maybe 10 years throughout like the DOE and internet industry companies. I presently work at Facebook. Oh yeah, sorry about that. So I presently work at Facebook, and inside Facebook I work on the Data Freeway project. And I've worked on some internals of HDFS as it relates to the Data Freeway project, as well as our distributed log collection systems, Scribe, Polygraphus, and also some real-time metrics. So as far as today, there's several things I hope to communicate. I'm hoping to give you guys a feel for where Data Freeway falls in data at Facebook. Hoping to convey some of the challenges around building Data Freeway, some of the constraints that make it an interesting problem. Give you guys an overview of the system, and also be able to dive into some of the details of the changes we made on HDFS. So I think the big thing here on this slide is just that we have a lot of data at Facebook. Many of these numbers might be as much as 6 months old, but one that's definitely up to date is the data rate, 4 gigabytes a second at peak. This translates to about 300 terabytes of data uncompressed per day. And so we've got quite a bit of data to handle here. And we have customers that want it both in real time and in batch systems. As far as what the architecture looks like, this is kind of your 30,000-foot view. I think the big takeaway from this picture is I want to give you guys a feel for the entry points and the exit points into the Data Freeway. So basically all the data comes in from one location in reality, or one system, and that's a Scribe data. Every single machine at Facebook, whether it's production, test, or a developer's box, runs a local Scribe data, and they can submit data to it via Thrift API. The largest producer of this data is basically our web tier, which also runs a local Scribe data. And most of that data is generated inside the PHP libraries, but nonetheless, it's really one and the same. And the thing to note about this data is the Thrift API basically just requires you to tag your data with a category, and then you can send an roughly arbitrary sized message. As far as exit points here, we have our Scribe NFS, which we're deprecating. I'll talk a little bit more about later. We also have the Scribe mid-tier here, which supports what we call direct send. That allows it to send to other services that basically mimic Scribe as far as their API. So people can have us directly send the data there, and they can implement the semantics they want as far as making it synchronous or asynchronous on the other side. Probably one of the biggest growing areas for data being consumed from the Data Freeway is this little p-tail bit here. And I'll talk a little bit more about it later, but basically it allows you to specify a category and get a stream for a category out of HDFS. There's also this Puma component I'll talk a tiny bit about, which is basically our real-time metrics system that we're working on. It's kind of going through a couple of different iterations. Lastly, the one is probably the one most people would be familiar with. We have a copier loader process that takes data from these waypoint HDFS installations and puts it onto our main warehouse cluster where it can be queried by Yahoo.
Question.
Yes, sorry.
Is the most traffic through Thrift or which?
Oh, sorry, yeah, very good question. The question was, where does most of the traffic go through? I think 250 terabytes goes through the p-tail and the Hive clusters, so not the direct send of the NFS, goes to the HDFS portion. NFS is probably 50 terabytes, and it's really a small amount that goes to the direct send. Some certain customers that have certain higher requirements. As far as the challenges, I've already outlined the data volume, but in addition we have data loss SLAs and latencies. And for loss, we try, in fact we actually meet a 0.01% loss. With respect to latency, our SLA is 10 seconds, but we can actually get that down to 4 or 5 seconds. It turns out to be difficult but achievable with some recent work that we did. And what I should mention is, sorry, jump back here. Latency is measured from when the data is generated on the web tier to being consumable from p-tail. So it's really the latency that consumers would see, not the latency to reach HDFS or anything else will actually be readable. And data loss is measured in our Hive clusters, again from the web tier, just as that's the historical source of truth. So now an overview of the system. First off, we refer to a system, part of our system as Scribe H, which actually doesn't include Scribe itself anymore, but used to, and now it includes this other system that works like Scribe called Calligraphus. HDFS is at the core of this system, not just ScribeH, but the core of Data Freeway. And it not only functions as a message bus, if you will, but also as a persistent and reliable storage system, so that if someone is tailing the message, being a subscriber, they can also go back and replay if there's some sort of error on their side. We also have what we call a continuous copier and loader, which basically is like a long-running, low-latency arson job that's constantly copying data from one cluster, from our various ScribeH clusters into our main warehouse. And there's a corresponding loader that actually makes that data available in our Hive query system. PTEL again is also here. I think that's what basically anyone who wants real-time data access through the HDFS path has to use PTEL. I mentioned Puma already. We're trying to make this into a configurable real-time analytics system. Here's another architectural view that emphasizes a couple other points. We have these web clusters, which are basically all our front-end machines, and they're the largest generator of our data. I'm not sure of the percentage, but probably at least 80%. And in order to be efficient with the network bandwidth, we actually have a ScribeH cluster located next to each front-end cluster. So basically what happens there as far as the data is the web tier logs the data, it goes to a local scribe D. That local scribe D will handle buffering in case it can't reach ScribeH. The data then flows on to ScribeH DFS. The copier process moves it into the warehouse again, so the loader can process it for query. And people who want to get the data in less than 10 seconds end up using detail.
Question.
Yeah, question.
Is that kind of a permutation of the pipeline HDFS architecture?
Sorry.
In other words, the HDFS architecture has the pipeline writing for multiple servers, right?
I'm sorry, I'm not following the question as far as what you mean. There's multiple HDFS clusters.
Right.
Yes.
But you basically get the data made reliable. Is that what you're doing here?
As far as why we, so are you asking why we have multiple HDFS clusters?
Yes. No, I'm asking, this doesn't look like the normal pipeline HDFS.
I'm concerned I'm familiar with what a normal pipeline should look like.
Oh, okay. All right.
Sorry, we'll go into it later. I'm happy to answer all the questions, but it's just not.
That's all right.
A little opaque.
Sorry about that.
That's all right. I wanted to go over some more of the details of the different pieces here. Maybe it'll become clear what's going on there. So the takeaways for Scribe for us, as far as what it is to the Data Freeway, is we consider it a reliable messaging framework in that it does the local buffering that I talked about before. So if it can't send downstream, it writes the data to a local disk and sends later. The other key point is that it's very, very easy to use. Because it's a Thrift API, it's language agnostic. Most of it does come from PHP as far as the data, but it can come from anywhere. And this is probably the major reason that we're doing about 4 gigabytes a second in data. I also want to mention this Calligraphus. This is what replaced the Scribe server within our ScribeH itself. And basically, it's a Java implementation of a part of Scribe that we were using in our ScribeH infrastructure. It speaks the exact same Thrift API and writes to HDFS in the same way that Scribe used to. As far as why we decided to go with Java, I should back up and say we were already going to extract this part of the code into its own standalone server in order to make it a little simpler and more reliable. And when we reevaluated what we were going to go along with, because HDFS is already in Java, we were talking about doing integration with Hive for streaming queries, perhaps. Java made more sense. We also wanted to avoid, we had some problems with doing JNI and libHDFS, some memory leaks, some status codes not exactly corresponding. In particular, we had an example where a list status call on a directory that was empty, or if the name node wasn't down, both returned to -1. You can imagine the applications can do drastically different things in that case. And of course, we fixed it, but it still was difficult to iterate changing Java APIs and having to go over it and modify the JNI. And hopefully we'll also be open sourcing this too in the coming months. And we'll also make clear how the two fit together more later. Also, so this is the funny part. As soon as we made Calligraphus a very simple part of Scribe, we wanted to make it more complicated. One of the reasons we wanted to extract some of the code for ScribeH out. We wanted to do this integration with Zookeeper. And for a moment, if you look at the diagram, the sort of first generation of Calligraphus or ScribeH didn't have Zookeeper or these writers or any policy database. It was just a symmetric tier of routers or just Calligraphus nodes that would write to HDFS. And if you do this, and you want to have them all writing at the same time, you need to make sure they have unique output paths on the HDFS system. And if you do a little math and say, hey, you've got 100 different hosts, maybe 10,000 categories, that's 1 million files right there. If you rotate those files, say, once an hour, in a 24-hour period, you've got 24 million files. We keep 3 days of data, that adds up to about 72 million files, if my math is right. And that's a lot of files to have on HDFS as far as the memory pressure on the main node. And so if we're going to solve that problem, we thought we would go this route. So basically what happens here is data comes in on these routers. Let me back up, sorry. There's this policy database at the bottom. And what happens is we have throughput information for the categories. And so on the zookeeper portion, we'll actually create what we call infrastructure buckets, which are they're basically a partitioning of a category stream. And they're just for internal sort of load balancing. What happens is these calligraphist writers will, all of them will participate in a leader election. It's kind of your standard zookeeper leader election where it basically boils down to a queue consisting of ephemeral sequence nodes. And it's two-phase though. So once someone's actually elected, they actually have to accept the nomination or what have you. And the reason we do that is the routers are also observing all these elections. And as soon as a writer actually accepts it, that's when they'll start sending in data. And you can imagine if you had, say, the top 10 in the queue all were not accepting the election, they were rejecting it in capacity, you would have a lot of sort of spray all over the place. You can get a little messy. One other comment I want to make is how the writers actually handle load balancing. It's not so much load balancing as they just maintain the invariant that they don't handle too much load. And that is they have a low watermark and a high watermark. And they accept up to the low mark and they will shed load at the high. And shedding is just basically if they are the leader, an activated leader in one of the buckets, they'll remove their node and put themselves back at the end of the queue. And failover is actually a generalization of shedding. Failover means if a writer goes down, because the nodes are ephemeral, once the session expires, which I think is about 10 or 15 seconds, the ephemeral nodes go away, and leader elections will ensue, and everything sorts itself out. Lastly, the routers actually buffer for these cases where temporarily things are out of whack. It's just memory buffer. But I wanted to talk probably the most about HDFS, and I think first it's good to understand why we wanted to replace NFS with HDFS. What's interesting for me, at least, is that I initially thought it would be related to cost, commodity hardware, with some filers. But apparently with the filers that this also predates me, but apparently with the filers they had, the cost per byte of actual storage turned out to be about a wash. And the major reasons that we ended up switching and migrating over to HDFS were two other ones. The first of which is network efficiency. If you'll recall, in one of the earlier diagrams I was pointing out, we have a dedicated HDFS cluster near the front-end clusters where most of our data is generated. And what we do is we can basically write that data to the cluster uncompressed or with something like QuickLZ to calligraphist anyway. And when we store it on HDFS or when we copy it out of the warehouse, we can perform something that feels a little better compression and maybe easier. And in this way, we can really cut down on the network bandwidth costs. And this will be copying like across data center or across region or what have you. So it's very expensive for us. The other major benefit that was actually probably the biggest one was simply for manageability and operations. If we wanted to add capacity to a filer, adding new volumes would create read-write hotspots and we would have to manually balance them out. With HDFS, this just goes away. And I think in the worst case, we had to run the balancer to smooth things out. This diagram is really just to illustrate something sort of how I look at how we're using HDFS here. It basically is showing how to view HDFS as a pub subsystem, mostly as a file system, but a little neatness here on the replicas. So the entities on the left-hand side here basically represent publishers. They send messages in and they just tag it with a category label. Anyone who wants to read messages for that category just starts up a detail instance and says, I want category 1. And they immediately start getting a stream of that data. They don't have to know about our file layout on HDFS. They don't have to know which machines the actual replicas are on, or even what cluster of our many clusters that the data is residing on. And yeah, so in addition to actually being a message hub, it's also, like I said, a reliable system that provides persistence and durability. So I'll get into detail a little bit more later again, but it allows you to do checkpointing so that if your process dies and you're able to save this checkpoint string that detail gives you, you can actually resume where you were. It sure be. Sorry?
That replica 1, 2, 3 thing, that's the pipeline part.
Oh, I couldn't hear that you said pipeline.
Yeah.
Yeah, I'll talk more about the pipeline.
No, you got it.
So that's how we wanted HDFS to work anyway. And stock 0.20 Hadoop didn't quite fit our needs. The biggest problem here is that for any given file, there's a set of blocks, and for a file that's being written to, there's what's called, I think this term's actually from 22 or trunk, but it holds here. It's the block being written, and that's not accessible for reading. And a block basically only becomes accessible once you close the file, in which case it's not a block being written, or if it rolls to the next block. And as a note, we typically use about 512 main size blocks. And even with our data rate, we can't roll those fast enough to meet our 10-second latency. So basically, this is what we need. We wanted to add the ability for our PTEL readers, or any reader for that matter, but particular PTEL with the 10-second latency, to be able to get the absolute latest data. Before doing that, actually, though, we needed to work on the writer's side. So for calligraphists or scribe or what have you, we had to have a way for the writers to make sure that data that they had written was actually visible. One was persistent, and two was actually visible. So HDFS 200 actually just implemented sync, or I think this is called H-flush on a trunk or 22. But the idea is that when sync is called, the first thing that a client will do is if the block that it's writing hasn't been persisted, it will send an RPC to the name node. The name node takes the targets for that current block, which are the hosts that's being written, that are part of the write pipeline, and persists them to the edit log. The next thing it does is flushes any of its buffers out through the write pipeline and waits for the corresponding hacks. And so the semantics are that when sync is returned, the targets will have been persisted to the edit log. And what that is that'll mean if the name node goes down and comes back up, they're still there. The block still exists. And all of the data has actually been written to the data node's disks. It may be in the OS buffer because we don't do file system sync or anything, but the odds are pretty good that it's persistent. Oh, one other note that we found in our experiments, at least with 20, sync is typically very expensive. I think the experiments were done with HBase and the transaction, the write-ahead log, and doing, I think, very frequent syncs, probably after every write, reduce the throughput to about half, which makes sense because you're spending most of your time waiting for this active pipeline. So moving along, once we had sync capability, this is when we had to make that last block actually available for reading. There's a couple of steps. The first step was, so when a client goes to open a file for read, it gets basically a list of located blocks, which are blocks for the file plus their actual machine locations. We augmented that with the targets, and targets again is just the locations for the last block. The client then has to do a second step, which is the data nodes in the write pipeline are the ones that actually know the length of the file current to that moment. So it actually contacts one of the data nodes and gets the length, and then it finishes constructing any client-side data structures for the file, and then it can go on and read the file. An interesting side effect to this that we actually just deal with in our PTEL client is that I haven't shown it here, but there could be, or there will be actually in our use case, 3 different nodes in the write pipeline, and they don't have the same length of the block on disk at any given moment. So you can actually read data from one data node, and if it goes down and you reconnect to another one, you can actually, the data that you read is gone. It hasn't been synced, for example. It's a little anomaly. We've seen it once that I know of, but it's something to kind of be aware of. So that problem wasn't a blocker, but this one that we encountered was we had to fix this one. The basic problem here is, or the basic situation is that HDFS writes 2 streams of data, sort of when you actually write a stream of data. It has this concept of a chunk, which is about 512 bytes by default, and that chunk has a corresponding 4-byte checksum. And it writes them to 2 separate files when they get to the data node. And what happens, of course, is that this is, I mean, a single disk write is not even atomic, let alone 2 files. And so if we now expose the reading of these 2 files, we open ourselves up to basically the second and fourth cases here, which would are basically when the checksum errors. The first and the third are okay, but in the second case, you'll actually get it's a metadata to data length mismatch. There's more data than there is checksum data. And in the last case, that's actually also true. There's more data than metadata, but you can't actually know how much data the last partial checksum is for. It's still just 4 bytes, so you get a checksum mismatch. So we fixed this in 2 different ways. We fixed it for our 0.20 append end branch, and we also did a fix in the trunk. The 0.20 sort of borrowed from some concepts in the H-flush implementation of the trunk, in that we have this concept of a visible length, and the visible length basically boils down to how much metadata we have. It's always less than data, since I commented before that data is always written first. And we don't actually bound the read by that. We let the clients read data up until the very end, but we know in case 2 and 4 here that we actually have to recompute the checksum for that last chunk. And in this case, we're avoiding regressions by getting rid of checksums or recomputing it all the time. It only happens in this very strict case here, so we're not going to have disks, blocks going bound if the checksum doesn't help us out. In trunk, we actually did this in a slightly more elegant way. There's already a visible length, and basically what we do is we keep the data for the last chunk and the checksum in memory. And in that way, since it's in memory, we can atomically change it, and anyone who tries to read it will get that last chunk from memory. I keep talking about the parallel Taylor. But there's really only a couple of things to keep in mind from this that I've mostly already outlined. It's a very convenient interface where you basically say, I want a string for this category, and it includes a -f option, which is just like a Unix tail, so that you can follow a stream. It also has some additional options where you can get approximate times, so you can say start approximately 1 hour ago, and it will give you data from there. But more importantly, when you want to do precise chunks of data, is this checkpoint capability it has. So if you tell it periodically, it will output in your data stream a string that can be used to reference that location. If this were actually a single stream on disk, this would just be the offset of the file. But because it's actually possibly hundreds of files, if not at least tens of files across many HDFS clusters, it's kind of a large string. And we've seen a high value of this as we tried to do some real-time analytics. The next piece I can talk about is our continuous copier. I think there's 2 real high-level points as far as why the continuous copier was important for us. Looking back, I can say previously we had an in-house sort of disk CP, basically an RC going on as well, and it was batch. We run it in a cron job. And the biggest problem with that, 2 problems. One was latency. If you ran it once an hour, you were going to have data up to an hour or more old. If you ran it more often, there would induce a certain amount of load by doing LSs on all our different name nodes. So the continuous copier lowers the latency, for one. We're getting data. There's some other issues that our warehouse doesn't have concurrent reader support or sync support. So we actually, with the continuous copier, can only make files available within the closed on the source side, which is our HDFS Scribe-H clusters. It also smoothed out network burstiness, right? Because we're not doing these batch copies, we're sort of continuously scanning the copy that you might see in there. It really helped out. And what's kind of interesting I found about this, it seemed like an abuse of MapReduce, but it turned out to be really clever, and it's worked pretty well actually. This thing actually operates far better. In that basically a continuous copier node is a map task. We basically are using the job tracker and the whole MapReduce system just to run a fixed number of map tasks. We want to guarantee that there are, say, 500 map tasks. Each one of these tasks has its own directory scanner for object. It also has some number of threads for doing directory copy, maybe 100 per task. And each node actually operates independently with the directory scanners, and they're basically looking at the source side, figuring out what needs to be copied, and they'll hand off directories to the directory copiers. We resolve the potential conflicts just by putting a write block on the destination side. So if 2 different nodes actually end up trying to copy the same directory, one of them will win and the other one will move on to try a different directory. This does require you to have enough directory copier threads to copy all the threads on directories on the other side, of course. And I just have a couple notes about Puma. Basically, it's a couple of different architectures we've tried to merge the real-time data from PTail with HBase to do different metrics. First generation architecture did most of the counters in HBase, and there's actually a production product that's using this. I believe I'm not sure what it's known to the outside, but it's called Platform Insights. We basically provide real-time metrics for application developers that use the Facebook platform. However, some of the metrics we're going next to with uniques and percentiles are a little bit more complex, and they're not suitable to doing directly in HBase. So we're actually making Puma in the first case was pretty much just a log parser, generate some keys, and then ship it off to HBase and do an atomic increment server side. Now Puma is probably going to be doing a lot more in-memory calculations and then using the PTEL checkpoint to do a transactional, or that along with transactional writes to HBase in order to have sort of precise flushing of data, which is another thing we're trying to figure out with some of our HBase guys, how to do some transactions on top of HBase. And that about sums it up. I think, again, a couple of takeaways to remember is HDFS is really at the core of this whole thing. Polygraphist and scribe are what gets data in, and PTEL and our copiers are how to get data out. And hopefully Puma will be developed and enhanced some more. Actually, I have one more quick slide. As far as where we're going in the future, a lot of our effort in the Data Freeway team is focused on this Puma project. So it may turn into some streaming SQL stuff, we're not sure. Right now it's just basically configuration driven, and it's a lot of sort of seeing how we can scale out these different architectures. Another thing that stalled a while back that we needed for this project was a seekable compression format. I don't know if something has come out in the last maybe 6 months that wasn't there, but the guy who's my manager was actually looking into this. And now he's a manager, he doesn't have time to do this, but he came up with this idea. It's pretty simple around doing container formats, and so hopefully we'll make some progress on that as well. Questions? More?
Since you've been trying to solve problems with HDFS, wondering why not using Cassandra?
Not using Cassandra for HDFS?
In place of HDFS, instead of HDFS. Because...
For HDFS, not HBase, you're saying?
Not HBase, no. Because you, correct me if I'm wrong, but you get very fast writes and reads, and I think you do not have that problem of blocking the block, write blocks, you can read it. So that syncing problem does not exist. And you do get I didn't do anything. It's just doing this. And you do get
is this short?
Yeah. And you do get to access the fields of data atomically and in a microwave. Right?
Yeah, that's that's really interesting. I haven't given much thought to that. Design decisions were made before I started working on this, but I would be curious, what sort of write throughput tends Cassandra as far as megabytes per second or what have you, gigabytes per second? What's the throughput per node that you can get? Is it really high?
My understanding and from my own experience, it's faster in performance than HDFS. I'm working on running an experiment to contrast the performance of actually a data mining project between Cassandra, MapReduce, and HDFS. Because the output, the throughput of Cassandra is supposedly much faster.
Yeah, I'm not aware. That'd be really interesting to hear about. As a company, I'm not sure where Facebook is going on key value storage, frankly, but just from a technical perspective, it wouldn't be difficult to plug something different in the middle there. HDFS for us is just serving as basically a file system for replication. Yeah, it would be interesting because I know that we're writing basically on the order of.
Petabytes.
I'm sorry.
Petabytes.
I'm sorry.
Petabytes.
Yeah, I mean, we're doing so basically we need to be able to flush somewhere on the order of 10 gigabytes a second, and we're not using that many nodes with these Scribe H clusters. So the throughput per HDFS node is going to be pretty high. It's in the tens of megabytes a second. Basically we saturate our links, so we have gigabyte links everywhere, and they're at so that's about 125 megabytes a second, and those are constantly full. So yeah, that's actually another point there. We haven't found HDFS to be a bottleneck. The bottleneck for our whole system is NIC resources. So
is it anywhere?
the NIC, the network interface card, so network bandwidth.
Yes.
So the ways that we're trying to scale this thing out focus more around using trading CPU for network, right? Can we compress it better?
That, if I may, leads me to my next question. Message back versus thrift. Message back protocol versus thrift. It's a protocol developed in Japan and it works probably on the order of 20 times faster. I was wondering if you followed with thrift only because it's a Facebook product, or did you not consider something else, or?
Yeah, that's just not an option there for all the RPC to Facebook isn't thrift, and actually, it's not the best choice at all for design here because one, it's synchronous, and two, some people are sending megabytes, 25 megabytes in a single message, and
yes,
that's very expensive to actually serialize it, send it out over the wire in a synchronous way. So yeah, thrift is not very good for the data transport protocol in the way that we're using it. But unfortunately, that's what we have to work with, at least on getting the data in. Once it's actually written to our systems, we just compress it as plain text. So it's not stored throughout the system. I don't know if I made that clear, actually. That's only the API to get the data into the system.
All right, question on the left over here.
Yeah, so you said that the latency between when something shows up at the web server to when something on the other end of PTail can use it is about 10 seconds. I'm wondering, is that because you're writing to HDFS and this is kind of a limitation of the concurrent read, or where's latency coming from? Because that's still larger than I would hope.
Yeah, I should have been clear though too. That's actually our 99th percentile. Oh, I'm sorry, yeah. So the question was basically why is it 10 seconds, right? That actually still sounds pretty high. And the thing there is that measure, I should have mentioned, is our 99th percentile. Typically what we see, and actually typically the 99th percentile is 4 or 5 seconds. I actually don't know what the average is or the median off the top of my head. Oh, that's not true, I take that back. In one of our more recent developments, it's typically on the order of 2 seconds. It's basically how soon you'll see data through there.
So is that because, like, there's, let me make like the scribe HDFS step is actually writing to HDFS, and you're kind of using HDFS as like a buffer point, essentially, between, like, PTail is actually reading from HDFS using this concurrent read. That's correct, right?
Yeah, so asserting that PTail is reading directly from HDFS. Yeah.
Okay. And like, so like, how much of the latency is there between when like a block becomes available? Is it just as soon as it gets written, and is there a large latency there, or?
I don't think actually HDFS is introducing most of the latency. So the question is more, it seems like you're getting at like where is this latency? It doesn't make sense yet. This is comparable to our NFS latency basically, and this is because the data is generated. So the timestamp will be generated, say, in the PHP code. There's the time it takes for that request. This is, say, a web request to serve your page on Facebook. For that actually to be processed, it's in a post-processing callback that it actually gets sent to Scribe on the local machine, on the local box. And most of the latency is actually probably here because Scribe tries to batch up some of the messages before it actually goes to Calligraph. I think it batches it for up to a second or a megabyte. And then once it reaches Calligraph also has another two-tiered approach where it's going to buffer things for a megabyte before it sends it to a writer. And the writer also has, we're calling sync every 7 seconds on HDFS. But in lieu of that, there's also another HDFS client-side buffer. I think a packet size is 64K or so. And so that can fill up for 7 seconds. So it's all these little buffers along the way, I think, that add up.
Last question, Sam? Yes, gentleman over there.
3 questions.
Actually, that was the last question.
3 parts. Let me rephrase. Thank you. You talked on that this data is uncompressed. Is it compressed anywhere in the pipeline?
I was just giving the uncompressed. So the question was whether or not the data is compressed anywhere. It's compressed throughout, actually. It's just most of our measures are uncompressed.
Okay. Next, in Puma, what's the kind of analytics you're doing in the real time?
So the question is what sort of analytics are we doing in Puma? The first were these basic counters, so just counters by demographics or what have you. The second are some variations of unique users per some sort of metric, or unique counts in general. And we'll probably be adding the basic sum count of percentiles, average what have you.
What is it that you're doing for BCP?
For
For BCP, business continuity money.
For which part of this? Yeah, I'm not sure how much I can add to that. Puma doesn't have a lot right now. We've taken some basic backups, I think. As far as the main part of it, the data freeway, sorry, I didn't repeat the questions around BCB, business continuity plans. Data freeway really doesn't deal with this too much because basically all of its data ends up in the warehouse. And I can kind of punt and just say, I don't know if the warehouse deals with that one. So, thanks.
Thank you, sir.